So, at its heart, electricity is the flow of electric charge, usually carried by tiny particles called electrons, moving through a conductor like a copper wire. That's the basic definition. Everything we do with electronics builds on this idea of charges moving in a controlled way. To really get it, let's break it down into the key players: voltage, current, and resistance. These three are like the main characters in every circuit story. First up, voltage, measured in volts, symbolized by V. Voltage is the push or the pressure that gets those electrons moving. Think of it like water pressure in a garden hose. Higher pressure means more force pushing the water along. In a circuit, a battery or power supply creates that voltage difference. One end has more potential energy than the other, so electrons want to flow from the negative side to the positive side. Next, current. This is the actual flow of charge, measured in amperes or amps, symbolized by I. Current tells you how many electrons are passing a point every second. Going back to the hose analogy, if voltage is the pressure, current is the amount of water actually flowing through the pipe per second. More flow means higher current. Then we have resistance, measured in ohms, symbolized by ohms. Resistance is exactly what it sounds like, the opposition to current flow. Some materials resist more than others. A thick, short copper wire has low resistance. A thin, long one, or something like rubber, has high resistance. In the hose world, resistance is like a narrow section or sand clogging the pipe. It slows down the flow. These three are tied together by one of the most useful rules in all of electronics, Ohm's law. It's beautifully simple. Voltage equals current multiplied by resistance. V equals I times R. You can rearrange it any way you need. I equals V over R, or R equals V over I. Let me show you with a couple quick examples. Imagine a circuit with 10 ohms of resistance and a current of 2 amps flowing through it. What's the voltage? Plug it in. V equals 2 amps times 10 ohms equals 20 volts. Easy. Now flip it. A 12-volt battery connected to a 6 ohm resistor. What's the current? I equals 12 volts divided by 6 ohms equals 2 amps. See how it works both ways. Okay, let's talk about energy and power next, because this is where things get practical. Power is the rate at which energy is used or delivered, measured in watts, W. The formula is P equals V times I. So if a device runs at 5 volts and pulls 0.5 amps, power is 5 times 0.5 equals 2.5 watts. Real-world example, that classic 60-watt light bulb on a 120-volt household supply. Current is P over V equals 60 over 120 equals 0.5 amps. Nice and straightforward. And here's a handy visual to lock in the water analogy for voltage, current, resistance, and even power. These show the pipe set up perfectly. Pressure for voltage, flow for current, narrow/sand for resistance, and flow rate versus total amount for power versus energy. Finally, electricity comes in two main flavors: direct current, DC, and alternating current, AC. With DC, the current flows steadily in one direction. Batteries, solar panels, your phone charger output, those are DC. Electrons keep drifting the same way. A C flips direction back and forth many times a second, 50 or 60 times in most countries. That's what comes out of your wall outlets. It alternates because it's easier to generate and transmit over long distances at high voltages, then transform down for home use. Here's a quick look at how their waveforms compare. DC is a straight line. AC is that smooth sine wave going positive and negative. And just to tie it all together, here's a simple basic circuit diagram. Battery, switch, resistor, or bulb, wires closing the loop. That's the foundation, folks. Electricity is charge in motion, driven by voltage, limited by resistance, carrying power to do useful work. Master these basics, and the rest of electronics starts making a lot more sense.